All right, okay. So you basically get the transpose of the matrix and then you multiply. Essentially, it's the same as matrix multiplication, except you have one additional step, and that's taking the transpose of the matrix. Okay, so now let's look at how we code our tensors in PyTorch. So first of all, you can initialize tensors in using 4 different ways. One is directly from data, which we will be showing later, and another way is if you have a NumPy array, right? You can convert that into a tensor, and you can convert one tensor to another tensor and initialize those values. You just have to preserve the properties, right? And after that, you can also create tensors with random values or values with constants. Okay, so first, before you code, you have to import the respective functions, right? So now we will be importing torch, which is the function that will essentially be converting, which we will be using to make the tensors and store the tensors. And the other one is NumPy. And NumPy is because we want to show you how we can convert a NumPy array into a tensor. Okay. Wait, before that, I want to change. Okay. All right. Okay, so if you input an array, you have an array of data, right? In this format where you have in the first row, you will have like 1 and 2, and in the second row, you have 3 and 4, right? You can use PyTorch torch.tensor to convert that into a tensor, essentially. And after that, here we do it with the NumPy array. You essentially get an NumPy array and then convert it to a tensor. I want to stress that using a NumPy array is perfectly fine. We are using PyTorch tensor because we will be using PyTorch for the rest of the way. You can technically code a full machine learning model using NumPy, and we have we have like a sample code for that inside this, but we will not be going into it. If you guys want to, you can actually go and look at it. Okay. Okay, what's next? Okay, here we are making a tensor by using the properties of another tensor. Now, x underscore data is a tensor that we've already made here, right? And we will be using the properties of that, the shape of the tensor, to make new tensors with certain other properties. Now, the first one, right, we'll make a tensor with the same shape, but all of the numbers will be 1. The next one, we'll put in random floating point numbers. As you can see, it says torch.float, right? So if we put in random floating point numbers into the tensor. And you can also define the shape and then use the shape as a basis to create a new tensor. Basically, the shape of the tensor, I will be going into it later. And as you can see, the first one is torch.rand. Rand means essentially, it means what, basically it just adds in random numbers, and ones just add in ones, and zeros just add in zeros, okay? Okay, so tensors have certain properties, right? And one of them is shape. Now, as you might have seen before, okay, so look at this, right? This tensor has a shape of 2 and 3. What does that mean? Well, it has 2 rows and 3 columns. And so some of these tensors, if you keep on increasing dimensions, right, you won't be able to tell them apart and say, this is a row, this is a column, right? So you just have to remember that the shape, the number of numbers in the shape shows the number of dimensions, and the number within each comma, right? Between each commas shows the maximum number of values in each of those dimensions. Okay, now moving on, the tensors, when they're storing, you can make them store certain data types. So the tensor that we've made stores float 32. There's float 16, and there's a lot of other data types. You can go and check the PyTorch documentation for that. And after that, you can, okay, the next one is tensor.device. Okay, this is very important in machine learning. We will actually be touching on this in Deep Learning 3, but for now, you can store tensors in your CPU. Basically, then your CPU will be doing the calculations on the tensors. You can store it on your GPU. Basically, when you store it on your GPU, right, your GPU will be doing the calculations. And the GPU is actually faster when it's calculating. Okay, so there are a number of operations that you can do on the tensor. So this operation is a slicing operation. Basically, you choose a column, right? You choose a column, and then you can turn that column into zeros, a bunch of zeros. Okay, so this dot means that this dot refers to rows, right? The first number before the comma refers to a row, right? And this means that it applies to all the rows, right? But what you're doing is you're turning the first column of all the rows into a zero. The next operation is concatenate, right? So what you do is you can use torch.cat to basically add tensors, join tensors together. Okay, and as you can see, this was the initial tensor, right? And we have attached 3 of them together here. The next one is transpose. It's very similar to the transpose that you have in matrix operations, right? So as you can see, the rows have been, the columns have been now converted into rows. So this column was this row was initially the first column. The second row was initially the second column. The third row was initially the third column, and so on. Now, okay, after this, we have multiplying tensors. So there is something called scalar multiplication, where you multiply a tensor with just one number. So what happens when you do that is that all the numbers inside the tensor will get multiplied by that specific number. The next one is element-wise multiplication. So what we are doing here is we are getting the first tensor and then multiplying it with the transpose of the tensor. So as you know, there's zeros in the first tensor, there's zeros in the columns. In the second tensor, there's zeros in the rows, in one whole row, right? So when you multiply, right, there's now in the new tensor, there's a whole row and a whole column which is 0. And the second operation is essentially the same. It's an alternative way of doing the same thing. And this one is essentially the matrix multiplication that I've talked about before. And these are the 3 different ways of doing that. Okay, so this is batch matrix multiplication. So now this tensor has 3 dimensions, right? But then matrix multiplication is for matrices, 2-dimensional objects, right? So what this one does is that it okay, so what this essentially means is that you have 10 different matrices, 10 stacks of matrices with this specific shape. So what this tensor does is that it considers each matrix separately and then uses matrix multiplication on those 2 matrices. So what you see is essentially the product. So there's like 10 matrices, right? 1, 2, 3, 4, 5, 6, 7, 8. Wait, I think I miscounted. But yeah, there should be essentially 10 matrices. And okay, wait. Sorry about that. I think I missed something. Ouch. Okay, so this does binary operation. Wait, I'll skip this part for now. Now, okay, so let's just recap what we learned in the last session, right? First, we talked about the whole process of how we make machine learning models. First, we get the data, right? We define the problem, and then we pre-process the data and clean the data. And after that, we set up the model, right? So we figure out what we need to do. It can be a regression problem. It can be a classification problem. We figure out what the problem is, and then we choose the model for the problem, for the specific problem. And then after that, we make the model, and then we fit the data in the model, and then we evaluate the model, and then basically we get the cost function, and then we update the model, keep on updating the model until it becomes better at what it does.
Can I have a question?
Yeah.
Can the people online pick me up? So I have one question. So why is there a sudden change in the flow of the presentation? We just learn about tensor, right?
Yeah.
And then now we jump back to machine learning workflow.
Uh-huh.
So what is the relevance? Why did you bring up the tensor?
Oh, okay. So tensors are very important in machine learning because you use tensors for all your training purposes. So tensor, okay, in computers, right? To program in computers, to make calculations in computers, you need numbers. So all the machine learning models that you use essentially use numbers. And what a tensor does is essentially store the numbers in specific places, right? And there are certain rules that govern how the tensor is changed, right? And basically, which is why it's fundamentally important to understand how tensors work, because you will be using it everywhere in machine learning. Does that answer your question?
Yes. And in the previous workshop, we are shown NumPy.
Yeah.
So why don't we just use NumPy array?
You could use NumPy array. It's perfectly okay to use NumPy array. I've already shown it to you. I said we can actually program code from scratch and make a machine learning model by just using NumPy. It's just that PyTorch just hides a lot of that complexity and just reduces your workload, so you can make more complex models faster and deploy them faster. Okay. All right. Okay. So last time we also talked about how the machine learning model takes in an input and then gets an output from the model, right? It does something. The model does something to the numbers that you input into the model, right? And then you get an output, right? And then you compare it with the label, right? And then you update the weight, right? So we will be touching up on all of that, essentially. And we also talked about what our aim is, right? When we are making a machine learning model. Okay. Okay. So now last time I think we spoke about regression, right? So we will be expanding on that concept, and today we will show you why we need deep learning, right? Now, first of all, just take a look at these numbers, okay? I mean, you can easily figure out what the first number is, the second number is. I know it's pixelated and all that, right? But you can easily say what the first number is, what the second number is, and what the third number is, and so on, right? But what if I ask you to like program it out? What if I asked you to code it out? Can you code out a way to distinguish this number from the next number? Can anyone do it? No, right? Because it's a very, very complicated problem. But this is where neural networks come in, and this is where deep learning comes in. Okay, so so for this workshop, right, we will be using a data set called the MNIST data set, and it's a bunch of pictures with numbers, a bunch of pictures with handwritten numbers, and the pictures are 28 by 28 pixels. So in total, you have around 784 pixels, and we will be working with that to explain how the machine learning model, how like deep learning works, fundamentally works. Okay, so now we have this number, right? And what we will be doing is we will be converting this into a tensor. I mean, we're coming back to that, right? We need it in number form, right? So we need to turn this image into a tensor, okay? So what we are going to do is we're going to assign some weight value based on how bright the color is, how bright the white color is, right? So if it's black, it's 0. If it's not black, if it's white, if it's very white, it will be a very high value, right? If it's gray, then maybe somewhere in between, right? So what we are going to do is we are going to assign values to those boxes, to these pixelated boxes, right? And then what we're going to do is we're going to take out each column, take out each row, and then we are going to attach them together. Something like this, okay? So now you have 784 like numbers, basically, right? So now you have numbers, and what you have to figure out is whether that number is showing 1 or 2 or 3 or 4 or 5, and so on, right? So now you have a bunch of data, you have handwritten numbers, and then you have labels for those numbers. So if it's a handwritten 9, right, you will have 9, a label 9 corresponding to that image. So how would you start solving this problem? How would you first like figure out how will you start solving this? Well, let's just expand on what we learned last time, right? We learned about linear regression, right? And this is essentially an expansion of that, okay? So what we have now is called a perceptron. A perceptron essentially has a few weights corresponding to the number of inputs. In our case, it's around 784. Yeah, 784. And then it has a bias, right? What you do is you multiply the inputs, the numbers, the individual numbers inside the tensor, and then you multiply it with the weights and add in a bias, and then you put that whole number that you basically get the multiplications and add them together. You get one single number, you put that number into an activation function, and then what you get is the output. The perceptron provides you an output. You have weights, you have biases, you take in the input, multiply it by the weights, add them together, get the sum, you add the bias also, and then you put it into the activation function to get an output. Now, it's very similar to linear regression, except for the fact that there is an extra additional activation function that you can customize. We will be going into the activation function eventually, but I want to first touch on why we need a bias and what purpose the weights have. Okay, now look at this. Take a look at this. So initially, what they will be doing is that they will be changing M, right? And you will see that this line is going to rotate. Yeah, so it's essentially rotating. And now when they change the intercept, right, the line is moving vertically, okay? So you can think of weights as the one that changes the orientation of the line or the plane or whatever in the tensors, right? And you can think of the bias B as the one that changes the location of the line and moves it along the y plane, right? So if you have like a problem similar to this, right? So if the only thing that you have are the weights, right? Your line will be stuck somewhere here, and the only thing that will be changing is the orientation. You do not want that, right? You want it to be cleanly here, right? In a linear, like in a regression problem. So which is why we need a bias. Now let's move on to the second part, which is the activation function. There are several activation functions with different purposes, right? One is the sigmoid activation function. As you can see, this is the equation of the sigmoid activation function. And what it does is that it takes the input and maps it between 0 and 1, right? And if you can, I don't know if you can see this, but if it's 0, right, it will be 0.5 here, right? And if it's slightly higher, right, it will the function will just shoot it up closer to 1, right? So as you move further away, right, it will be like perpetually at 1, right? So if it's after 5 to like infinite, right, any number beyond 5 should be very, very close to 1, right? And any number beyond -5 should be very, very close to 0. And there are other activation functions. The ReLU activation function, essentially, if the number is less than 0, it will just cancel off the number, essentially makes it 0. If it's more than 0, it will just keep it the same. And then the next activation function is the tanh function. The tanh function is similar to the sigmoid function, but then the tanh function maps it between 1 and -1. And then finally, the last function is softmax function. And this function is a nonlinear function. Basically, what it does is that if you have multiple things and you have to classify those things, right, you can put it into a softmax function, and it will give you like essentially something like a probability, right? So the sum of all those numbers will be 1. Of the different things will be 1. I mean, you can try using this equation and try figuring it out. So if you have 1, 10, 15, and 20, right, you can just try it out. The sum at the end, after you get all those values, should be 1, okay? Okay, so what is the purpose of these functions? Essentially, these functions help you figure out if one neuron is active or not, right? So if the number that you get out of it, right, is actually like slightly more than 5 or something like that, right? So it'll automatically just push it up to 1. If it's slightly less than -5, right, let's just push it up to 0. And it's a similar case to tanh, but then you have -1 and 1. These functions do have some issues, but we will not be going into it. You can read it later. There's some interesting stuff, vanishing gradients, saturation, and we will be touching on that in later workshops. Okay, but what is the issue with having this single perceptron? Okay, this is called a sigmoid perceptron, or now I think it's called a perceptron. So what is the issue with this single perceptron? Well, it's very good at figuring out patterns that are just flat and linear, right? It's similar to a regression function, right? It's too simple. You can figure out linear patterns, but what if the pattern is much more complicated? Okay, so to solve this issue, right, what we do is we add in more perceptrons. Okay, so before that, it looks complicated, but it's not that complicated. Now, this, as you can see, is a perceptron. So these are weights, and there is a bias. The bias is not, you can't see it essentially, but you add that, you get these numbers, multiply it by the weights, which are the arrows, you add in the bias, and then you put it into an activation function to get a number here. Okay, So you get numbers in like using the same technique in all the other perceptrons, right? And all of these different arrows are different weights, okay? And you can intuitively think of it as a filter, okay? So if you think of the image of this number, right? You can think of it like a filter that, if you think, you can think of it like a filter that filters, basically pushes these values up and pushes these values down. And if the filters match with this number, it'll essentially say it's 1, or else it'll be 0, okay? And then what they do is they add in more perceptrons to map out more complicated functions. So this is essentially a deep neural network. Why is it deep? Because you have multiple layers, multiple hidden layers in between the input layer and the output layer, okay? So why do they use it? Why not just one perceptron, right? As we saw, the perceptron can only figure out simple relationships, right? What if the relationship was more complicated? What if it was a circle? What if it was like in like more dimensions? How, like, so how does this solve the issue, right? For that, I would recommend going to this website. Okay, you can actually go to this website and you can play around. This website is very good. It's essentially a book, but it's online. It's in website form, and here they demonstrate how a function like this can be turned into a step function. So, okay, so if you take a look at this, right, you can play around with this. Okay, so you can play around with the values here, right? So, and see how things change, okay? So basically the fundamental point that I want to make is that having these multiple layers will allow you to make complicated functions that one perceptron cannot make. So now we have the effect of having perceptrons in parallel, but also in series, right? Perceptrons on top of each other and also perceptrons working with each other. Another way to think of it is, okay, so let's say that we have a bunch of we go to Netflix, right? What we have, we can have different genres, right? One can be like a TV series, one can be like a talk show, one can be like a reality TV series, and one can be like an animation or something like that, right? And those different genres will have subgenres like sci-fi or something like adventure or something like, you have different genres, right? You can think of it, you can think of the first line as those big portions, and you can think of the second line as those small portions. Now, okay, so okay, so now let's go into the math. Now you understand that you have a perceptron that can, that can classify data, and you have a multi-layer perceptron which has multiple perceptrons in parallel and in series that help you figure out any kind of complicated function, right? So we will go into the math of how these numbers work. So now you have an input, right? And this input is a tensor with one column, right? And 4 rows, right? And you have 2 perceptrons, and those perceptrons have 1, 2, 3, 4 weights. The first perceptron has 4 weights. The second perceptron has 4 weights. And then what you do is you add in biases to both of those perceptrons, and you send them through an activation function. Usually it's like sigmoid or whatever activation function that you choose, right? So this is basically what we've demonstrated here. So we've multiplied this with this, and we've added the bias. So now, as you can see, this belongs to the first perceptron, and this one belongs to the second perceptron. The second row belongs to the second perceptron. And then you send it through F, which is the activation function, to get A2. And you have two of those, right? You have two of those. So this one is A2, right? A2 has two rows, right? And those rows represent this, the outputs from this and this. And you can do that again and keep on doing that to get to make like more complicated functions and to get more complicated values. Okay, now let's code. So how do you incorporate all of that? How do you incorporate all those tensors, all those perceptrons, and how do you make them into this one model, right? Well, we are using Torch because the PyTorch essentially has a lot of hidden functions and a lot of hidden features that take away all the complicated math, all the complicated mess, and makes it very, very easy for you to make a neural network model. So first of all, we have initiated all the functions that we need, so we are importing Torch and all the other things that we need. And after that, we are defining. Okay, just ignore this part for now. Okay, so now let's look at what these mean. Okay. This bit defines the model, how our model will look. Okay. So as you can see, the first one is 28 into 28, right? That's the size of our picture. So now we've flattened it. We've opened it up as one long tensor, right? So that's the first layer, right? So we have this picture. We've opened it up, right? And then we have to have another layer. We have another layer, right? And we have to figure out the weights, right? But PyTorch does it for you. So what you have to just say is how many tensors you have initially, the input layer, and then how many neurons you have in the hidden layer, in the first hidden layer, right? So first one has 784 in the input layer, right? The second one has 16 neurons, right? In the first hidden layer. After that, we are mapping 16 to 16. We chose this arbitrarily just to show you, right? And after that, it'll be 16 to 10. Why 10? Can someone tell me why it's 10? Yes, exactly. So first one maps to the first hidden layer. Second line maps from the first hidden layer to the second hidden layer. And the last line maps from the second hidden layer to the output layer, which should give you the numbers, whether it's 0, whether it's 1, whether it's 2, to like whether it's 9, right? Right. So let's just run this. Okay, now let's look at this part. This part shows you what happens to the input. Okay, first, X is your input, right? You basically change this input so that it's 1 into 784, right? And then what you do is you put it into this first layer. The first layer, all the mappings, all the weights are there, right? And then you get the answer, and then you put it into the activation function. The activation function that we are using here for the model is the sigmoid activation function. And then we get the X again, right, as the output, and then we put it in to the next layer. And then what we get out, we put into the activation function again. And then what we get, we put it into the third layer to get the final value. And that's the number that you get at the end. Okay, so here you have the NumPy version of the code. I will show it to you, but I won't go through what it's doing. Okay, you can, if you want, you can go to this link and check it out. We will be sharing this notebook later. So essentially, all of this, right, is a compressed version of this that purely uses NumPy to train the model. Okay, so basically what PyTorch is doing is hiding all that math, all that extra steps for you so that you can actually make more complicated, bigger models more easily. Okay, so essentially what we want the model to do, right, is that if we put in a 9, any kind of 9, any weird looking 9, right, and it should give you tell you that the answer is 9, right? But of course, we have not trained it, so it's a mess. All the weights are unknown, right? So what we will get is this utter trash. So how do we go from getting all these random values, right, to getting the specific value, getting the right value, right? That's the next step in our process. Okay, before that, we have 784, right? So 784 should all map to all of these different perceptrons. And then all of these different perceptrons have to map to all of the other perceptrons and then to the output layer, right? Guess how many weights we have to figure out? Well, turns out it's 13,000. It's actually 13,002 weights and biases. So we have to figure out the value of 13,002, right? And we are going to look at how we are going to figure it out. Okay, so we do this, we accomplish this task by training the neural network. Okay, so first of all, what we will be talking about is forward pass, and then we will be talking about the cost function / loss function, and then we will be talking about gradient descent, and we will be talking about backpropagation and so on, which is all under training the neural network. Okay. The forward pass is essentially when you put in one data, right? One of those images, right? Of handwritten like digits, right? We put that in to the neural network, and the neural network makes a prediction. So what's happening is this. So basically we get a prediction. So we get all of these different numbers, right? That's essentially, that's basically it. That's a forward pass. And each of those layers will have matrix multiplication as you've seen. So because each of these is a perceptron, right? So you can multiply the weights to get one number, and each of those numbers are put into another set of weights, and then we get another number, and at the end we have like a bunch of numbers. Basically, we have to figure out all the numbers. Okay, so you will get a random output, and you have to figure out a way to make those outputs not random. Okay, so first of all, you have to figure out a way to measure how bad the output is, right? First of all, you have to be able to tell the model if the output is utter trash or if it's perfect, right? So that's one thing that you need. That's one tool that you need. The second tool that you need is a way to improve the weights so that you can reach the output, right? So we can define that whole thing using this mathematical formula. Okay, you do not have to remember this mathematical formula, but it's just for your knowledge, right? This is called arg, right? The argument function. Essentially, this is a condition, and the argument function finds the input value that satisfies the condition, that best satisfies this condition, right? So we have arg min b, and this is the function that defines how well your model is performing, right? So the minimum means this one should be minimum, right? So we have to ensure that this function is minimum, and the b that ensures that this function is minimum, right, is this b. So we have to figure out a way to make this loss function minimum, and you have to figure out the b that makes this loss function minimum. Essentially, when they're talking about b, we're talking about weights and biases, right? So what is a loss function? Yeah.
So what is the big N?
Oh, big N is the total number of the total number of outputs. Wait, sorry. The total number of data points, right? So basically, this is essentially measures the loss of the total number of data points, basically.
Yes.
Yeah.
So how do we determine this number of data points? What is n?
Oh, n is essentially the number of data that you get, right? That you have in your hand, right? And then you use this function, right, to figure out the n for all of these, right? And then you basically figure out the b for that. Okay. Okay, moving on. Okay. Now, okay, so this is what we have come up with to figure out how badly or how well your model is performing, right? So there are multiple different kinds of loss functions. So for a regression problem, right? A problem where you have to have like a range of numbers from 0 to some other number, and there's no discrete numbers, right? You use mean square error or mean absolute error. A mean square error, I think you've already seen this for like variance and all that. It essentially measures basically it compares the number to the mean, right? And so on. And then this is the cost entropy loss. And basically what this does is you have 1 minus yi, and basically you use log to measure the loss, and then you get the average of that.
Can you repeat? Just now you said for the mean square error.
Yeah.
What is y and what is y hat?
Y hat should be the mean of the bunch of outputs.
Are you sure?
Yeah, it's for a selected number of outputs, right?
I think so. Why, right? So there is an output of the model.
Yeah.
And there is the label.
Yes. Oh, yes. Okay. Yes. You compare it with the label of the model. Yes. Okay. I'm sorry about that. So what you get is the output, and then you compare it with the label of the model, and basically you square it and then you sum it up to see how badly or how well your model is performing. And for the classification part, you also use the label of the model, but then it essentially helps you classify it by making it into like 2 discrete digits. Okay. So you have a bunch of weights and biases that you have to figure out, right? And you have you have one number that comes out from the cost function, right? And then you have to minimize that cost function by adjusting the weights and biases, right? So you have to essentially make the function the lowest as you can make it, right? So it's very similar to finding the lowest value of a given function in trig, right? So basically what you do is you take a point, right? You take the point and you differentiate at that point. You basically find the gradient of that point, and you go in the opposite direction of the gradient to go to a number that's lower than the existing number, right? And if you do it enough times, you will end up at the bottom of the function. Okay. So this is the principle that we will be applying in training all of these weights. Okay. So we will be finding the gradients basically, and we will try to move in the direction opposite to the essentially in the negative direction of the gradient to get to the minimum possible value. But it's not that simple. So you have extra steps that you have to finish. Okay. Okay. So what happens is that if you move too fast, right, you will completely miss the lowest point, and your model will start like behaving erratically, right? And then you will not find the minimum possible value of the weights. So you have to be very careful when you are moving down the curve. You have to make sure, you have to ensure that you are moving slowly when you have to move slowly, and you move fast when you have to move fast. So the tool that you use to adjust that is the learning rate, and we will be going through that in the next workshop. So here's a meme about finding the global minimum, but yeah. Okay. So now what we have to do is we have to find the gradients of the output related to different weights, right? So that we can change those specific weights, right, at the correct amount of value. So you can think of it like this. You have a bunch of weights, right? And when you change each of these weights, right, the outcome, the loss of the model will change differently, very differently. So some weights can be moved more compared to others to make the loss less. So your aim is to tweak the weights as optimally as you can to make sure that the loss that you get, right, by inputting the label and the output of the model, right, you have to ensure that you tweak the weights in a way that this becomes zero. This goes as close to zero as possible. Okay. So how do we do that? Well, we have to find the gradients. Okay. So we have to find. Okay. So for those of you who already know, right, this means a small amount, right? This is essentially what this equation is referring to is what change will happen in the loss function when you tweak a specific weight by a small amount, right? So if it's WL, right, it refers to tweaking this specific weight, and it refers to how much this will change when you tweak this specific weight, right? So if this was, let's say, ZL, right, then it will refer to how much tweaking this weight by a small amount will tweak the other weight by a small amount, right?
Can you describe what is happening in this image?
Oh, I will get into it. Wait, hold on. So what we have to do is that we have to get all of these values for all of the gradients for each of these weights, right? And then we tweak it by a certain amount. So these different weights will have different gradients, right? And then we multiply it by a certain amount, right, to optimize this function, basically. So now hold on. Okay, so how do we do it? We use something called the chain rule, but before that, okay, so we have a loss function, right? And when you tweak this part, right, by a small amount, what happens is that
What is the loss function?
this part is the output of the, yes, the output of the loss function, as you can see here, right? Okay, so when you tweak this part,
can you also use the mouse so that?
Oh yes, okay. Okay, awesome. When you tweak this by a small amount, right, this will get tweaked by a small amount. Do we agree on that? Because in a perceptron, think about it, right? You tweak this the function that's previous to it, a weight previous to it, before it by a small amount, C gets tweaked by a small amount, because when you change it here, it's connected, so it gets changed there, right? Now, why? Okay, now let's expand on that, right? You tweak Z by a small amount. What happens? This is connected to Z, right? Right? So when you tweak Z by a small amount, what happens is that A will also get tweaked by a small amount. And that A will eventually go and tweak this by a small amount, right? Okay, so we can keep on expanding that principle, right? You tweak W by a small amount, right? What happens is that this function that's before it, right? The function that this goes and feeds into tweaks this by a small amount, right? This function in turn goes down there, tweaks this function by a small amount, and that tweaks it by another small amount. The only difference is that this might be, you might have to move this more compared to this to get this change, and so on, right? So a gradient tells you how much is this compared to this, how much is this compared to this, how much is this compared to this, right? Okay, so we can actually calculate the gradient of this compared to this, the gradient, this compared to this, and this compared to this. But then that's not what we actually want. What we actually want is this compared to this compared to this function compared to this, right? So to do that, we use something called a chain rule. So the chain rule takes advantage of the fact that this is linked to this, and all of these are linked together, right? All of these along that line are linked together, and the chain rule takes advantage of that. So you divide this by this, you get a certain gradient. You divide this by this, you get another certain gradient, right? It will essentially look like this, okay? So you divide a small change by this, you change this by this, you get one gradient, and you get another gradient for this, you get another gradient for this. And then what you can do is you can multiply them together to get the gradient of this output function, right? The loss function, compared to every individual weight and every individual bias that you have in your neural network, right? So now that you have all those gradients, what you can do is you can move in those specific directions opposite to the gradient, the value of the gradient, to minimize the function, right? So that's essentially backpropagation. So first of all, you have to find the gradients. We've established that you have to find the gradients to actually minimize the loss so that your model actually makes the right predictions, right? Next, what you have to do is you have to figure out the gradients of all the different weights relative to your loss function, right? Okay. And then what you have to do is you have to move slightly in the direction. And what these different gradients do is that if the gradient is big, it'll move the weight further. And if the gradient is small, it'll move the weight by a smaller amount, right? And then gradually what happens is that if you keep on doing it again and again and again and again, what will happen is that you will reach a point where the loss is as low as possible or close to as low as possible, right? Right. So this basically demonstrates backpropagation. And so now you have gradients, and you essentially, this is the code that we will be using to demonstrate what we've been talking about. Okay, let me run this first. This might take some time. Oh, okay, so while this is running, right, you guys can take a short break. Yeah. Okay.
So now maybe we will take a 10-minute break because it's also half the time. And so as you have seen that we have go through all the necessary component in slides or in the pictures. So the next part will be the code, and we will show you how to actually use it. So now, yeah, take a break, take toilet break. If you have questions, if you want us to elaborate on the slides, do raise your question. Yeah, so I was talking to the people in the room, but it also applies for the people online as well. So if you have any questions, if you want us to expand on the math or explain any visualization that you are not really sure of, do raise a question.
Okay, so the question is, how do you tweak all those weights, like 13,000 weights, right? Okay, so I will go back and talk about backpropagation again. And then I will link it back to how we will use that to tweak the weights in the neural network. So first of all, you know that what you have to figure out is how each weight influences the loss function, right? Right. So, but what you can measure is the change to the loss function compared to the preceding weights, right? And so on. And the change to the next neuron compared to the preceding neuron, the preceding weights, right? And the change to this neuron compared to the previous one, right? So what you use is the chain rule to figure out the gradients related to different weights, right? I think you understand that part, right? Do you? Oh, okay. Sure.
So I will open two notebooks. So yeah, the question is how to actually update them. And so I will, yes, I will open two of them because I think it is easy to, it's easier to see the different interpretation of the same thing. Or yeah, so first, the idea of gradient of changes. So as you can see in this equation, is your partial differentiation, right? Differentiation. So partial difference, previously when we learned differentiation is, let's say, dy over dt. So dy over dt, how y change with a change in t. So more than t is only one value. Here we have multiple weights. So if you can see in this bracket, partial differentiation of c over x is x1 all the way to xn. And each of the weights in the neural network is an element in this array. So if there are like thousands of weights, then the m will be like thousands in the thousand. So that is the idea. We want this term. We want the gradient term, right? Gradient, partial differentiation, they're all connected. And so So first you can see that, okay, so partial differentiation nearer to the endpoint. So C, how do we calculate C? C is the cost function. We calculate it at the very end. So here on the graph over here, you can see that we have, share. Okay, I should have shared the screen. I'm sorry for online people. Yeah, so I was sharing both screen at once. So I was referring to the equation and how it like maps onto the it maps onto the graph, the diagram, right? So each of the arrows is a weight, and we want to find the partial differentiation of the cost over all those weights. If the weights are closer to the output, it is easy, like you have one step. But if the weights are like all the way nearer to the start, so that is where the idea of chain rules come in. So you don't just like do one step back, but multiple step back to trace all the way back. Yeah, so the idea is you find the gradient by doing partial differentiation. So now you have the gradient. What do you do next?
Yeah, sure. Okay, so what you have, as we explained, thanks. What you have is the gradients of every specific weight, right? So let me get, okay, so what, okay, so here I think we can understand, you can think of okay, what if the weight was here, right? So you have to get the gradients, you can get individual gradients, it's not that hard. You can compare it with the preceding one, right? And you can get individual gradients, get gradient here, gradient here, gradient here. You use the chain rule to figure out the gradient of this one compared to the cost function, this one compared to the cost function. And you do that for all of these gradients, right? So you have partial differentiation essentially for each of those weights, right? And biases. And what you do is you move at a certain amount along those different gradients. Yeah. So basically you move, you basically you are doing this, but at a very, very large scale, right? So it's not this function, but you have like thousands of these graphs that need to be going down to the minimum, right? It's very hard to visualize because the number of variables is very high, but you can think of it as reducing, you can think of it as tweaking towards the direction in a way that C becomes as small as possible, right? So it's an expansion, it's an extension of this idea, right? But you have multiple gradients that now have to be upgraded, now have to be like tweaked so that the C becomes as low as possible. Is that okay? Okay.
You find the final gradient, C with respect to the first one.
Yeah.
What do you do?
Oh, you move by small amount. So you multiply it by a certain amount and change the weight. So you basically use this equation, the same one. You basically use this equation, the same one, to you update the weight. So you use this equation to update each of those weights using those partial differential equations, essentially.
And when you said, okay, there are thousands of weights, how do we update them all at once? So that is the amazing part of the PyTorch library. So this part, yeah. So as you can see, I'm now recalling the idea of object-oriented programming. If you have catch the previous workshop, yes. So now we are initializing a class that we define as MLP, right? So this class is based on top of the PyTorch libraries. And in this PyTorch libraries, they all give us it gives us a tool to update all the weight at once. Yeah.
And it's done underneath. So you don't see any of the code. You don't see any of it happening. You do not see like all the multiplications, all the divisions, all the steps that need to happen. It's not shown to you, but it happens in the background, right? So basically what it it makes it easier for you to focus on what's important, but it handles all the repetitive tasks, right? Essentially what a program ideally needs to do. Okay.
And that is what we'll be showing you next as well, the code, the implementation. So the slide, the images, the visualization that we presented was the core idea, the key concept. So now as practitioner, we're not researcher, we're not doing them from scratch. We're practitioner, and we will see that in action.
Any other questions? Anyone? Anyone online, especially people online? Okay. All right.
To put the data in the model, first we have to normalize it. So that it like the function, like it's in the range of the function, for example, -1 to 1 or like 0 to 1. Or is the data set already normalized?
Oh, okay. A nice question. Okay, so you're asking if the function, the thing that you input has to be between 0 and 1, right? Or 1 and -1 or something like that, right? Okay. The thing is, the activation function essentially maps all the numbers that you put in any range to 0 and 1. So it does it for you. So you can input a data essentially having any range, right? You do not have to normalize it. You can just put it in,
So
basically.
the data we're passing into the function is basically the RGB values.
In this case, it's not RGB. It's just one color, right? Black and white, essentially. So we use the intensity of the white to calculate it. But then beyond this, right, as we go on, we will actually be tackling RGB values and all that. But for this one, it's actually intensity of the color. So it's just one number for one pixel. So if it's black, it's 0. If it's white, pure white, then it's just one maximum value. And if it's in between, there's some in between value that's been selected for the model. Yeah.
Last question.
Yeah.
For the activation function that you're using for this case is the sigmoid. So how do you like decide which of the activation functions to use for a specific machine learning?
Honestly, you have to look at the type of the problem, and there is some research that they do, and part of it is just you test it out and see if it improves the performance, and you try things out basically in practice. Do you want to add something in?
Yes, can they hear me
You can-
all the way?
Yes, so we try to,
I think it's close.
so we try to give you an idea, the big picture, the various components. In each component, in each concept, there are multiple techniques, right? Deep learning is still a very active and very what is the term? Yeah, it's still in an active space, both in an engineering perspective and a research perspective. The research perspective, they will keep coming up with new things to. So activation function is, let's say, a box, right? What is inside the box? What do we actually use? People are keep being research. They are continue to research. On the engineering side, yes, they will take those research, test it out to see if it improves performance or not. And that is also the idea behind why do we break down the deep learning into like 3 parts as well. So the first part, we just run through the big picture, like the various important components. The subsequent parts, we will expand on the various intricacies and what are the possible options that we can choose at different stages. What do we use? Why we sigmoid, and why do we choose softmax or all these kinds? And actually, right, the idea of normalization that our friend just brought up. So he was asking, do we need to constrain the data to any particular range, 0 to 1 or -1 to 1? The fact is that there is no hard rule. It is not like math where you say you cannot divide it by 0. This is, I think, can be think in terms of, let's say, an engineering problem. You have a range of things that you can try. then as you try, you see that, oh, if I constrain the data into this particular range, it still works or it improves performance. Then you just use that range. So there are a lot of try and errors, and depends on the different problems that you're tackling. So for example, if we're dealing with images, if it goes from 0 to 255, right, your 8 bits, then some people will just leave it at 0 to 255. Some people will say, actually, we want to squeeze it into like 0 and 1. Some people say, okay, let's just explode it. Let it explode into like 1,000 or million. But doing so will have their own problem, and it actually becomes a problem in deep learning 3 that we also have planned for that as well. We are dealing with the idea of floating points.
Yeah.
Right, floating points, how data is stored in the computers, and that will have big impacts on how the machine learning will perform. Yeah. So the idea is there are various variables that can go wrong, and as practitioner, yeah, what do we choose, right?
Yeah.
I guess popular opinion. So after a while, you will see people convert into various popular activation function. So maybe they would want to do like the ReLU or like leaky ReLU. So those are the popular ones. There's
Softmax is also used, right?
Yes.
Transformers.
and the softmax and some. So you can see that, for example, ReLU and leaky ReLU, it goes from 0 to infinity. But softmax and sigmoid is like constrained in 0 and 1. So there is an application specific activation function. 0 to 1 usually correspond to the probability, but the ReLU and leaky ReLU is like, yeah, I just want it to explode to infinity or large range. I don't know how it will turn out, but probably it will work, probably. So as you continue to learn, you will see people picking up, let's say, the best practices or the popular ones. Yes. So we share with you the basic concept, and it is always like recommended to also find some popular GitHub and see what people have done and build on top of that as a learning process. Yeah.
All right. Okay. Okay, so let's look at the coding part. We left off at the coding part, right? Okay, so initially what we did was we basically coded out the model, right? So we defined how the model is going to look like, and we defined how, when you put in some data points, right, how the data points will be processed to get the output that you want, right? Next, what you have to do is essentially you have to apply all of these now in code, right? So that to get like a properly trained function. Okay, so what I did was during the break, right, I actually ran this function, right? It took a while to run, if you guys noticed. So essentially what is happening is we are loading the data set, which is the MNIST data set. It's very popular. And then we are getting like the training batch, training set, data set, right? We will go into how this processing happens later in the next workshop, if I'm not wrong, right? We are using this loss function. Okay, now let's go back. We are using the cross entropy loss function, right? So we are using the cross entropy loss function because these are distinct values, right? 0 to 9, right? You have to figure out whether it's 0 to 9. Next, we are using the optimizer. It's stochastic gradient descent, which is gradient descent, but you use. Continue.
Yeah, continue.
Oh, okay.
Yeah, continue. I think you can split into two.
Oh, okay.
Right.
Okay. So basically, we're using stochastic gradient descent, which essentially means that you get like a batch of data and then you calculate the gradients together. So what is happening here is that first, you define how many of those how many times you want to send the data through the model and how many times are you planning to like update the model, right? So we chose 35. It's actually arbitrary, and we will be talking about how to choose these numbers later. Initially, we get the data, right? We get the inputs and the labels from the data that we loaded previously, right? So now we have the inputs and now we have the labels, right? What do you have to do with the inputs? We get the inputs and then put it through the model and get an output so that we can calculate the loss, right? Right. So now what we do is we are essentially doing that. We are making the gradient 0, right? And then what we are doing is we are getting the outputs of the model by using the input. Initially, it's going to be random. Initially, it's not something that you can use. And then you get the loss, and then there's backward propagation. It's all hidden under the code. All that complicated stuff is now hidden under the code, right? And then you move one small step, right? One previously designated step. You move all the weights and biases by one small step so as to reduce the loss function as optimally as possible. So if you do it enough number of times, right, what happens is that, as you can see here, right, the loss gradually starts reducing, right? As you update the gradients, as you get the values, the loss will gradually start reducing. And now the loss is 0. If you do some more times, it might go down. Okay, so now that we've trained the model, right? Now we've updated the weights. Now we've done all the stuff that we've talked about in programming, right? We will see what we have come up with, okay? Okay. So now So as you can see, the model has predictor. So the red values are values where the prediction is wrong, and the green values are values where the prediction is actually right. So initially, what we had are numbers, and we did not know how to program them out, how to code it out so that we can tell different numbers from different numbers apart, right? And now we made the model, and essentially what we have is this. And some of these cases, right, you have to cut it some slack because look at this. Is it a 5 or a 6, right? And then some of these actually look like a 9, right? And in some places, the model does make mistakes. But as you can see, this is very surprising compared to what we had, right? Initially, what we had is just something that's random, something we couldn't actually figure out we couldn't actually predict what the outcome was. And now we have these numbers. Okay, so now we spoke about the weights, right? So I want to show you what those weights look like. Okay, so we have 16 perceptrons, right? So now we have the weights. Okay, so we had 784, right, input values, right, that we stretched out and then put it into a model, right? Now I've gotten all the weights, right, and then I've brought it and made it into an image, back into an image, right? Now this is a 28 by 28 image, right? And these are the corresponding weights. Okay, so each of these perceptrons, the weights of each of these different perceptrons look very different. And when you actually start learning about CNNs and all that, you will see that some of these weights actually start forming patterns and all that, essentially like a filter. We will not be going into how that happens. We will be doing that later. But as you can see, right, this thing that was initially completely random has now made something like this. And if you look at the next layer, right, from 16 to each of those individual perceptrons. So you have 16 weights, right? 4 into 4 weights. And this is how those 4 into 4 weights actually look like. if the color is more intense, that means the value of the weight is really high. If the color is less intense, that means the value is less intense. It's essentially all these are numbers. I just put color to them so that you can see actually like what it is. You can feel what it is essentially. But these are actually numbers, weights, numbers for those individual weights. Okay. Okay, this is the last meme, but okay. Before that, I want to summarize the whole thing one more time. First of all, we define what a neuron is and what it does, right? So a neuron has a bunch of weights. All these arrows correspond to a weight, right? Those weights, each of those weights is multiplied with each of those inputs, each of those input numbers that are given to the model in the form of one tensor, right? 1 into 784 tensor, right? In our case. And then there is an additional bias where you add the bias to the weights, right? And then you get one single number. So you add these all up, you add that up, and you get one single number, and you put it into an activation function, and then you get an output. After that, what we did was we looked at the importance of biases, right? The importance of having weights, importance of having biases. And then after that, we spoke about the different activation functions. So what the functionality of these different activation functions are and what they do. And then we spoke about this, how we can use multiple neurons, one either in parallel and you can stack some of them on top of each other to essentially make any kind of function, any kind of complicated function that you can think of. Please do go check this website out. It's very helpful. Like it's very clear. They've clearly written it out. And of course, after that, we spoke about this is the math part. And then we actually built the model, right? The model, we learned about how we can actually put in the weights. We can actually define the weights by just visually by mapping from the input values to the first hidden layer, and then from the first hidden layer to the second hidden layer, the weights for the first hidden layer to the second hidden layer, and then from the second hidden layer to the output values. All of those weights, as you make this and run this, right, all of those weights are now like initiated by PyTorch, and they have it underneath in the program. And what you do not have to create new numbers, you do not have to create new weights. PyTorch does it for you. And then we looked at how the initial input goes into the model, right? What process it goes through. First, it goes through the first layer, and then goes through the sigmoid function, goes to the second layer, gets multiplied by the weights, goes to the next sigmoid function, and finally you get like a bunch of values after it goes to the final layer, right? After that, we spoke about how we train the neural network. So first we define the goal of why we are training the neural network. The goal of training is to minimize the loss function as much as you can, so that your model makes an as accurate as a prediction that is close to the real thing, right? Close to the label as possible, right? So first we mathematically define what our goal is, and then we spoke about the cost/loss function, where we actually compare the output of the model with the label of the model. And then we talked about how you can minimize a function, right? You find the minimum value of the function, right? And the loss function shows you how badly the model is messing up, and you have to reduce it as much as possible for the model to perform well. And then we spoke about gradient descent. We spoke about going down the hill by small steps every single time until you get to the low point. And then we spoke about how to calculate the different gradients with respect to each of the weights and biases, right? And then we essentially use the same technique, but now you get the to get the gradient, you have to do one extra step, and that extra step is essentially chain rule. You use the chain rules to figure out the individual gradients, the gradient of the loss function with respect to the individual weights and biases, and then you basically tweak them, and gradually, when you tweak them, you will essentially, what you are aiming to do is end up in the lowest spot possible in the function, in the loss function. And then we did the training. We spoke about, we loaded the model, and then we took out the inputs and labels. We sent the inputs into the model. We got the outputs, and then we did back propagation, and then we updated the thing. And all of this is done underneath by PyTorch, right? So you do not have to hard code any of it. All of this is given as like handy functions that you can use. And then we looked at how well we've trained the model, right? And as you can see here, the numbers, a lot of these numbers are correct, right? And when it does mess up, right, some of these cases are very hard for us, even humans, to actually like figure out. Like example for this one, right? And then we looked at how the weights look like, right? How the numbers actually are different. And then finally, we are wrapping up our course. We've actually given a lot of like useful links within the course, so that you can go back and refer to them. One of this is the YouTube channel called 3 Blue 1 Brown. They have a very good series. So if you do find it hard, if you can't understand what we've shown you here, you can actually go back and refer to that channel. And another good source is actually this one, where this person actually does makes the model from scratch using NumPy, right? Which you can see is huge. Yeah, so basically, this one is also pretty good. So you can go back and refer to it, and then essentially that brings us to the end of the workshop.
Yeah, thank you, Danush. And I just want to try to make interesting connection as he was sharing. Because let's say he has already shared the code from scratch, right? Like code the neural network from scratch. So I think if we look into this, there can be interesting thing that we can pick out in order to see what is happening. Backpropagation. Backpropagation. Actually, okay, never mind. So yes, so on the practical front, what are the big important code is this cell on, yes, this cell, this model initialization cell. How we define the multi-layer perceptron model. So first we do the initialization of like a Python class and follow the various function that is given nn something. So if you can see the import torch dot nn import torch optim. Yeah, how do we even know to do this thing? You go to the torch library, and then you can follow the documentation, and under the documentation, then you can see all the various options that you can use. Here we are introducing the linear layer, the simplest form, but as you go along in our series, you will find other layers for different tasks as well. other layers, other activation function. So this block is for the model definition. So if we go back all the way, look at the big picture, right? Let's say, look at this big picture. Then this code block on the left correspond to the gray box on the right. So all the model is contained on the right. So how do we train? How do we train then? So the training part comes from the second code section. So this code section, you can see that at the start, we prepare the data. So this will correspond to your blue square in the X. Here, you might look like, okay, there are like only 3 lines. That looks simple, but it is not simple because this MNIST data is a popular data. It is one of the tasks that originally, when people first tackling the problem of deep learning, they use it very frequently. The number of data point is very small, like less than 1 million. So it can be saved in the cloud. We can pull it out quickly. It is even, okay, you can see dataset.mnist. So it is actually a part of the, it is already defined inside the PyTorch library. We just call the function. So this is, again, an example so that we can introduce you to the world of deep learning. In reality, it will be very, if not very important, to write your own code to import all these images. We will not share here, but as you go along, if you're interested, you can come to us for advice. Especially, there will be a project at the very end in semester 2. So the idea, right? The idea is that you have to store all those images. Let's say you have an image. You have to store all those images in a folder, right? And how do you label the image, right? Let's say there's a cat, there's a dog. There's a cat, there's a dog. How do you label it? You might think, okay, let's put that in the name of the image. So cat 0001, cat 00002. And what if you have millions of it? So cat 1 million. That is quite impractical. And furthermore, nowadays, if you know that there are like self-driving cars and a lot of data labels, so it is very impractical to save the images with the label as a file name. Therefore, they will have a separate file to save all those label points. So the task of preparing data, like this 3 lines, is a simplified version. The task of preparing the data is to write down all your Python code, to search the folder, snatch the photos over here, map it onto the different file, and snatch the label on the corresponding file in order to get your inputs and labels. So it is a more involved process. If you're interested, yeah, come to us, communicate to us now, here, after the workshop, or in the future. Just keep in touch and we will share more. For the sake of the workshop, we want to keep it brief and introductory so that you can have a good sense. We only use the the readily available data set. So that will be the preparation of the data. That will be the blue part. So next is the training loop. So you can see that there is the model definition, and there's the training loop. So the training loop will oversee all the arrows that you can see, that you see on the right illustration. Yeah, so this loop is the thing that handles all the things that we have shared today, from calculating the cost, from back propagation, and do updating of the function of the weights. So this will be your training loop. Yes. And beside the training loop, we also, another point that you can see is that even though we print out the photos and images, right, they are not really understandable, right? We don't really understand what is happening. So another key component as a practical implementation is to always log it out, log, visualize, many steps in the process. So you can see that there is, yeah, this is the simplest form of logging, just print out what is happening at what epoch. But as you go further, there are other logging tools for you to see more information about your machine learning training project. I'm not sure if you have heard about this, but weight and biases. There's a company called Weight and Biases. Yeah, the same concept that you have shared. So in this weight and biases platform, yeah, you can see they log a lot of things, right? Oh, like which weights go into where, how many parameters, what is the budget like for our machine learning project? How is the loss function, decrease over time? So yes, logging is a very crucial component in machine learning, just for us to make sense of what is happening, what is really happening. Yeah, and here it is simplified as just a print. So it is good enough as a starting point, but and I do encourage you to keep on the lookout for various interesting visualization tools. And at the very end is to cross-check, double-check, validate if the model is is good enough. So for example, in this case, right? Yeah, is this model good enough as a hand recognition model? Probably, because there are only a few reds out of a sea of green output over here. So probably it is good enough. And
you can actually improve it, right?
Yeah.
Eventually, because you can tweak the epochs and
yes. So yes, as just now, like one of the questions that we were asked, there are many things that you can tweak and adjust. They are called hyperparameters. So hyperparameters are, in a meta level, like your step outside of the action. So the parameters, you can call the parameters are all your weight and biases, but hyperparameters is something that is not really a part of the process, but definitely affects how the process will turn out. For example, like he said, I put 35 because, arbitrary. I use this optimizer SGD because as an introduction. But these different components, there are a lot of other options to choose from. And that is another practical consideration as well. Which one to choose? Follow the best practices, follow the most popular ones. And yeah, the research community will constantly pumping out papers and recommend, what is the best practices. So yes, so those are the two main code blocks: model definition and the training loop. I hope you know them by heart, knows what is happening. And in the later workshop, that you can swap in and swap out various options, but they will generally stay in the same place. Yeah, for example, if I said so now we are doing classification, but if we do regression, criterion, then probably it will be nn.mse. Yeah, so it is just a substitution. It's just a matter of substituting the correct hyperparameter. So today we give you the backbone. In the future, when you are more confident, you can sub in, sub out, and play around with more freedom. Yeah. So do you have anything else to add on?
Should be it. If you guys want to actually jump into the sea and see how big things are, have you shown like okay, so there's this website called so if you guys want to jump in, so there are a few, like they list out all the newest papers and all the best papers, right? If you guys are interested and if you want to see how what new research is coming out right now, right? You can actually go through this website. So there's something called state of the art. There's like so many different things that you can go into. If you go to those websites, you can see their implementations. But then that's like in the future, right? For now, I think we need to focus on how to the next few steps, which is what you have to do next, like choosing the hyperparameters and how you do it. This was not just this, but it was like a more complicated database. How do you load the database and stuff like that? But for now, I think that should be it.
And yeah, so that will be all of the content. We are just, adding more interesting fun facts. And I hope you can give us a feedback for our presentation as well as trying out the quiz as well. So the quiz is, just to reiterate for those who are not aware, the series, the workshop that we're conducting, in the previous years, it used to be, isolated workshops for people who are interested. But now in our year, we are making it into a series, trying to build up the competence of the members, of the people, of the participants who are following us, all the way up to a comfortable level, right? So therefore, we have all these quiz as a checkpoint for them to really understand and make sure that they understand the process. So these quizzes are our cost function, right? We use the quiz as a cost function to see if you have been, if your prediction match the labels. Yeah, that is quite a lame analogy.
Yeah, I don't think it worked out.
But yes, for those who are not a part of our LEARNOVA's member, you might not follow us all the way through, but I think trying out the quiz is also a fun way to refresh your memory of today's session. Again, the recording, the feedback is already in the recordings, but it's okay. It's okay. We will reward, like if people watch the recordings and go reach this stage, I reward it. So the feedback actually give them bonus points for the whole learning journey. Yes. So that will be it for everything. Yeah. So even though we don't use slides for this workshop, I think we will try to make, let's say, a summary slides so that you can browse through. Yeah, after the workshop. Yeah.
Also, if you've been to like previous workshops, if you guys actually prefer slides, do let us know. Like put it into the comments, so that we can gauge what you guys like are looking for in the future for future workshops.
Yes, that will be it. And yes, you have question. How do you choose the number of, so another question, how do you choose the number of nodes? So that again is another hyperparameters that you can tweak and find out. Yeah, so he will be mentioning about this point, this stage over here. So it is not just about how many nodes, it is also about how many layers. Yeah, in one layers, how many nodes are there? How are they all connected? Again, that will scale, that will be a consideration depending on your task. And also it depends on your task. And then you cannot explode, you cannot just keep attaching the nodes indefinitely, because there will be, it will reach a state where there is a diminishing returns. We might think that, oh, if all of these nodes allows us to do complicated tasks, does that mean adding more layers means that we will do even more complicated tasks, like all the way up to, let's say, advanced intelligence? No, sadly, no. There will be a diminishing return based because of the numerical, the inherent numerical calculation that it has to carry out. And if you recall, all the gradients has to be back propagated and at each state, the gradient will have this idea of vanishing gradient. So at some point, it will just be 0. So effectively, it's not updating anything. So that is the issue of the various architecture. You cannot add them all the way for too long. But yes, that will be another discussion. It will be in the topic for another day. But yeah, be aware that, you know, it is a hyper parameter. It's something that you have to decide how many. Yes, that will be, let's say that will be in this stage. So again, if we try to map into our machine learning workflow, that will be new model, new hypothesis. You think adding more layer is better, you try adding more layers, run the whole thing again, see if it is better or not, then do it all over again. Yeah.
So at the end of our predictions for the handwriting,
Yes.
we found some abnormalities because of user input. Like suppose you write a 4 which looks like a 9.
Yes.
The machine learning model can't do anything about it. So is it advisable to remove that data set, like the data point itself, or is it advisable to keep it there? Because then if there are many of them, then the accuracy will decrease.
Yes. So is it advisable to do so? I would say, so now, because because we are trying to use deep learning to tackle a real life and messy problem, right? If you recall, okay, I cannot keep saying if you recall. So last time we are dealing with tabular data, and if the data is bad, there is missing data, we know that the data is bad and we can clear it out because it is missing. But for our case, since we are trying to tackle a difficult problem, there is uncertainty in the world. Maybe the bad handwriting is inherent in the world. It is maybe a valuable data. So so again, the line between whether it is a good or a bad data gets even more blurry. And it also points to this idea of machine learning as well. Machine learning ultimately boils down to this. I'm sorry. Yeah, a machine learning ultimately boils down to amount of data that it's sorry. It boils down to the if it sees a lot of data, it will work very well. And it is a probability thing, right? It is yeah, it is a probabilistic model. The more it sees bad handwriting, the better it is at recognizing the bad handwriting. So this will, so the question that you raise is about the data collection and processing pipeline. There is again, I think that there is no like clear-cut answer, but it is something that we have to keep in mind. Yes. So you might say, so just now, the one point that he raised was, we want to increase the accuracy, right? But do we want to, you know, cheat the system to gain arbitrary numbers, you know, 100%, or do we actually want it to operate well in the world, in the uncertain world, right? Yeah. So there is like always a trade-off, always a consideration.
Yeah, but what if like someone's handwriting is actually really bad, but then that person can't tell if it's a 5 or a 6, right?
So at the end of the day, at the moment, right? Even with the, let's say ChatGPT is trained on the same idea, same concept. And we, of course, we have this idea of training the AI to become super intelligent. But to be fair, at the moment, it is more like, you know, average, you know, because it learns from the internet, it learns all the good and all the bad. And the output that it gives us is like, you know, average, run of the mill. Probably it is good as, you know, suggesting recipe, or like, yeah, can give you some point for your essay as well. But those essays are also quite average, I would say. definitely a better writer with years of experience can beat it quite easily. So the AI, the AI that you design have to also match the task that you want to tackle. And ideally, there should be another, a human expert to, correct the errors of that model. Yes.
I think we can wrap it up now.
Yeah. So
Uh,
that will be, I hope you can, so now that will be all for the workshop today.
Yeah. Okay. So, the important thing to remember is that you need to remember the intuition of what's happening, right? I mean, you might forget the mathematical equation. I mean, you guys saw that I've